We want to evaluate the given double integral over the region D, where D is defined here. D is a region where x squared plus y squared is greater than or equal to 25 and less than or equal to 49, which means the region of integration would be the area in the xy plane bounded by these two circles, where they're both centered at 0. One has a radius of 5, the other has a radius of 7. So because our region of integration is circular, we're going to write the double integral in polar form in order to evaluate it. When converting a double integral from rectangular form to polar form, we need to write f of x comma y as f of r comma theta, meaning we need to substitute r cosine theta for x and r sine theta for y to get a function of r and theta, and then differential a, which is equal to dx dy or dy dx in rectangular form, is equal to r dr d theta in polar form. Before we set this up though, let's take a look at the graph of f of x comma y, the integrand function, in space over this region in the xy plane. We'll first take a look at the integrand function in a smaller window, which we see here. It gets much busier when we take a look at it in a larger window, which we see here in blue. And now if we look down on the xy plane, which is graphed in yellow, again, the area we're integrating over in the xy plane is the area between these two circles. And notice how if we look down on this area, we can see that the blue surface given by f of x comma y is both positive and negative over this region, which means the double integral does not represent the volume bounded by the surface in the xy plane over the region of integration. Of course, we can still evaluate the integral, it just does not represent volume. So going back to our work, again, we know that f of x comma y is equal to cosine of the quantity x squared plus y squared. But we need a function in terms of r and theta for the double integral in polar form. So f of r comma theta would be equal to, well, x squared plus y squared is equal to r squared. So we just have cosine of r squared. So now we'll set up the double integral in polar form. So we'll have f of r comma theta, which we now know is cosine r squared. And then we have r dr d theta. And now we need to find the limits of integration for r and theta that would trace out this area in the xy plane. Well, notice how the radius r would be from 5 to 7. So the limits of integration for r are from 5 to 7. And then to trace out this area, we'd have to rotate one full revolution, which would be from 0 all the way to 2 pi radians. So limits of integration for theta are from 0 to 2 pi. Now that we have our double integral set up in polar form, let's evaluate this on the next slide. Notice how to find the antiderivative with respect to r. We'll have to perform u substitution. We'll let u be equal to r squared, and therefore differential u is equal to 2r dr. Notice how we have r dr here, so let's divide both sides by 2. So we have 1/2 differential u is equal to r dr. And now to help us find the antiderivative, let's write this in terms of u. We would have cosine u, and then r dr again is 1/2 differential u. So with respect to u, the antiderivative would be 1/2 sine u, which means with respect to r, we would have 1/2 sine r squared. And again, the limits of integration are from 5 to 7. Let's go ahead and rewrite this as 1/2 times the integral from 0 to 2 pi. And now we'll evaluate sine r squared at 7, then 5, and then find the difference. So we'd have 1/2 times the integral from 0 to 2 pi of, when r is equal to 7, we have sine of 7 squared, or 49, minus, when r is 5, we have sine 5 squared, or sine 25. And sine 49 minus sine 25 is a constant, so we could write this as 1/2 times the quantity sine 49 minus sine 25 times the integral from 0 to 2 pi of d theta, or 1 d theta if we want, which is going to give us the same constant, and the antiderivative is going to be theta. So finally we have, again, this constant times, when theta is 2 pi, we have 2 pi. When theta is 0, of course, we have 0. So the exact value of our double integral, notice here we have 1/2, and then we have times 2 pi, that'd just be pi. So the exact value would be pi times the quantity sine 49 minus sine 25. Let's also get a decimal approximation for this value. We do want to make sure that we are in radian mode, which we are. So back to the home screen. So we'll enter pi, open parenthesis, sine 49, close parenthesis, minus sine 25, close parenthesis, and enter. And we get approximately negative 2.5805. I hope you found this helpful.